So not just NP hard to do the full optimization. Oh no, 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 nothing so nice as that. I'm not going to find any. I mean, it's the very simplest things you could come up with like that are already NP hard. It's like, okay, trying to come up with proof with algorithms that are provably correct and provably run in polynomial time and everything. It ain't going to happen. Like this is what I should have been using all along. Kind of bitter pill for those of us who are systematizers and who like all the theory to be nice, in that sometimes just throwing lots and lots of computation and data at the problem will solve it. What asked me to do that was nobody else was going to do it. The author was dead. Anyway, so that was not intended to be a career boost or anything. It was just sort of a passion project for me. And it turned out to get me my entree into marketing research. Now, I don't know if you've ever done this, but turning academic code into production code is kind of a nightmare. You have to understand the math to understand why it's a bug. Most practitioners don't really get into the fine details of measure theory. But measure theory is really cool in the sense that it unifies.
All right, so today I'd like to welcome Dr. Kevin S. Van Horn on this podcast. Kevin has been in this industry for a little while. His doctorate thesis was on how learning is really a big optimization problem. And since then, he's worked in many companies across different industries, including search, online advertising, done a lot of work, kind of more of a consulting places like Savvy Sherpa. And also, Kevin has had an opportunity to teach computer science at several points in his career. Kevin was a colleague of mine at Adobe. I learned a ton from him. I think he is one of the greatest Bayesians that I've seen, whatever that means nowadays. And today, Kevin has his own company where he helps businesses kind of navigate through, how would you say this? The uncertainties of ML in production. And specifically, yeah, go ahead.
Yeah, Bayesian statistical modeling.
Yeah, I'm going to cut that out and I'm going to pretend like I knew to begin with. Specifically, Bayesian statistical modeling, and he does a lot of work with mixed marketing modeling and lots of stuff for marketing. Well, I'm not sure that was any better. I'm going to have to cut a lot of this. But anyway, welcome, Kevin. And would love to ask you how you see your career, primarily from this, from the perspective of like, what are the main things that you've learned? What have kind of the more pivotal points in your career been, and how you ended up where you are now?
Okay. Well, I will try to mostly focus on stuff that is relevant to ML and data science. So I started off getting degrees in physics and computer science. I always say that physics was my first love, uh, but I wanted to build things too, so I focused on computer science. But part of all of that with both physics and CS is that I always wanted to understand things at a fundamental level. There's a certain personality type they say is the what do they call it, a systematizer, right? The one who wants to see the grand scheme, who wants to see how it all fits together, what are the basic principles and so forth. That's me 100%. And so that has always been my approach to pretty much anything I've gotten into. Is like I want to make sure that I like understand what's really going on. It's in some sense. So when I my graduate work at BYU, I got interested in machine learning. Got interested in neural networks at that time. And so, of course, the big question to me was, everybody was talking about generalizing in that time, Oh, neural networks can generalize. So what in the world does generalize mean, right? So I wanted to make sure I understood that. And so I began to look into some of the literature on machine learning at that time. And this is early days. We're talking about 91. Okay. pretty early days in some of this stuff, and got into something called computational learning theory, which actually mixes together statistics and computational complexity, and found myself having to learn a lot of statistics and teaching myself that. And gradually over time beginning to get a feel for, oh, okay, this is, in a real sense, machine learning and all this stuff. It's in a sense all statistical problems, right? Not the traditional statistical problems, which were always like narrowly um, um, limited to specific models with a finite number of parameters and so forth, but attempts to do things with much more complicated models. But there are certainly some very, very strong common ideas in there. Um, so, as you mentioned, my initial dissertation was on machine learning as optimization. And in the spirit of computational learning theory, I tried to prove positive results and couldn't. Uh, it's really hard to come up with any sort of positive results in that field. It's a lot easier to come up with negative results, which I then turned my attention to, and prove some rather discouraging negative results. Okay, so let me tell you the two really discouraging negative results that I got. Okay, what's like the simplest kinds of machine learning or inference problems you could think of? Well, how about a simple linear discriminant function, right? You just linear threshold function, right? That should be easy, right? Well, okay. Also known as a one level neural network, right? Or the single unit, single level neural network. Well, it turns out that if you want to minimize the number of inputs that you pay attention to, right? Because there's all kinds of, you could have a large set of possible predictors you could look at. You could look at interactions between them. You could look at various functions and so forth. So this whole business of, like, the optimization side of it, if you need to reduce the number of inputs to reduce the difference between your empirical error and the actual error. That problem is not just NP hard. And I assume your audience knows what NP hard means, right? It means, as far as we know, there's very, very good circumstantial evidence that you're never going to find a polynomial time algorithm for it. They're all going to be exponential blowups in the amount of time. So not just NP hard to do the full optimization. Oh, no, 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 nothing so nice as that. It's NP hard to even come up with any constant factor. So he's like, I'm okay
I
with coming up
love
with
it. I love it
50%.
I love it when stuff starts with "It's not just NP hard." Uh,
Yeah. So it's like, you tell me that you're okay with coming up with within double the minimum number of inputs. Sorry, to get it perfect. By the way, to get to zero error, and we get into something similar if you're just trying to minimize the error. Okay, so if instead you're saying, okay, I'm not trying to optimize or minimize the number of inputs we're using, but I'm trying to minimize the empirical error, right? The misclassification error. Well, again, it's NP hard even trying to come within any constant factor of minimum. So if you say, I'm okay with double the minimum empirical error, that's NP hard. 10 times, that's NP hard. So that was pretty damn discouraging at that point. So at that point, it's like, okay, I'm not going to find any. I mean, it's the very simplest things you could come up with like that are already NP hard. It's like, okay, trying to come up with algorithms that are provably correct and provably run in polynomial time and everything, it ain't going to happen. And so the rest of my dissertation, I did some work on learning classification rules, but that was all very empirical. That was all much more in the sense of trying out um, various more intuitive ideas. Nothing guaranteed to work, right? But that works often enough. And by the way, before I go on, I'll probably get back to this later on. But that's an interesting thing we run into, is that we keep on running these situations where if you want guarantees, you're forget it. You can't get guarantees. But often we find that we can come up with solutions that work very often.
Yeah, I was actually going to say
You know,
that probably prepared you for ML as it is in real life better
yeah.
than anything. Yeah, I think that's an interesting topic to explore. But yeah, um,
So
after you graduated, I mean, it's not like ML was everywhere at the time, or
no,
was
no.
it?
No. And there's a lot of talk about data mining and so forth. So it took a while before that really took off. And so I really did get a chance to work in what I had done my dissertation topic on, those kinds of problems for quite a while. Um, but one of the things that came out of it was that right towards the end of my dissertation, I learned about the Bayesian approach, Bayesian probability, Bayesian statistics, and it was kind of like this is what I should have been using all along because it solved so many problems that I had with the more traditional classical frequentist approach. It was far more general, could answer far more general set of questions than what I could with the other tools.
Interestingly enough, I
But
had the same experience years later when you taught me about the Bayesian approach, and I was like, "Oh yeah, why weren't we doing this?" So yeah, you passed it on.
yeah, so that kind of I remained interested in that for quite a while. From about 1997 to 2000, I worked in a speech recognition company. It was called Phonics. It was a startup, and applied some of the Bayesian stuff there. Um, One of the interesting things that I found in there was this was my first introduction to the kind of bitter pill for those of us who are systematizers and who like all the theory to be nice. In that sometimes just throwing lots and lots of computation and data at the problem will solve it. And they were seeing this with hidden Markov models applied to speech recognition at the time. The hidden Markov models for speech recognition have been around forever, but they're
Mhm.
starting to get some real results because they just had tons of training data to use with it. Um, Going on further from that, I got into some of Edwin Jaynes's work on Bayesian probability theory, specifically his book that came out in 2003. But I read the precursors to it, the unpublished version before it was published, and a number of his papers. Learn about maximum principle of maximum entropy. Learn about Cox's theorem. What are the reasons why probability theory is the right way to reason about degrees of credibility or uncertainty, all that stuff. And I created a page of my own, which is still up there. It's pretty old now. It's really old school HTML, but it's my unofficial errata commentary on Jaynes's book, which was published after he died. Um, his former student sort of cleaned up a few things and published it. Well, um, that turned out to be my entree into getting into some more interesting stuff because in 2009,
Sorry, I'm going to press a little bit more on that. What on earth possessed you to write it?
to write it,
Yeah.
because I was
Because all of us
very
have ideas, right? Like when I read a book, I'm like, oh yeah, they're like I have a bunch of ideas. I do not go and publish them on the internet. So
what possessed me to do that? What possessed me to do that was nobody else was going to do it. The author was dead, right? And there were errata, and I thought that his book was a very, very important book, and somebody needed to do it. And then, of course, the commentary was, well, as long as I'm doing this, I do have some commentary that might provide some additional explanation. I might as well put that in there too. Anyway, so that was not intended to be a career boost or anything. It was just sort of a passion project for me, and it turned out to get me my entree into marketing research. So several years later, when I was looking for work again, and during most of the time, I had not actually been able to get work doing pattern recognition, machine learning, data mining, data science kind of things. But I one of the like 100 different places that I applied to was a marketing research firm, and the VP of software development. When he found my webpage, he internet stalked me, And when he found my webpage, he basically said, "This is the guy. This is who we're looking for." So I did not intend that to be a resume, but it was. And so what the modelers did, they later got consumed by a huge company called Omnicom, if you can believe it. The name sounds ominous, you know. And it really was, that company really was like this soup of half digested companies that they had bought up. They were not fully integrated yet. But anyway, what the modelers did is that in marketing research, um, there's a lot of math, actual real math and real science and real statistics involved in modern marketing research, analyzing the data. And one of the kinds of things that marketing researchers are interested in is they want to know your values, what you as a consumer are, when you want to buy a certain class of product, how much you value different possible features or different, uh, uh, and how you do the trade-offs between them, right? How they trade off, in particular, what they call willingness to pay, which you can think of as, if you're familiar with microeconomic theory and the idea of utility, decision makers have this utility function and they maximize expected utility. What they're trying to do is they're trying to infer the consumer's utility function, and they want to do it on an individual level. But part of the problem is that they can't ask enough questions to really pin it down for any individual. So anyway, let me back up a little bit. People can't tell you what their utility function is. Okay, they just can't. They can't give you a number. They can't really they can't tell you. But what they can do is they can make decisions. That they know how to do. So what a lot of this marketing research stuff does, at least in the area of what's called discrete choice surveys, discrete choice modeling, is they will create a bunch of hypothetical purchasing scenarios for the survey taker. And these hypothetical purchasing scenarios, they'll have 3 to 5 hypothetical products described by some set of attributes, things like price, things like if it's a computer, like how much memory it is, or screen size, or if it's a car, maybe it's gas mileage, or what its internal volume is, or things like that. Okay, and so that's what they use to describe these various hypothetical products. And then they put these before the survey taker and say, well, which of these would you buy, if any? And then from their answers, assuming that they are acting as reasonably rational beings, with a little bit of noise thrown in there, they then infer that utility function for them. And so then you can do all kinds of fun things once you've got that, right? Once you've got that, you can now predict, or at least try to predict, what their choices would be in other scenarios. So you can say, okay, well, I know the competition has this product and this product. There are these products already out there. What if I bring in this other product here? How will it fare against the ones that are already out there now? And so you can sort of predict what their choices will be. You can also segment the market based not on demographic attributes, but on what you really want, which is based on their desires, what they're willing to pay for, what they're looking for in a product. So all kinds of fun things you can do with that. And some of the Bayesian methods help you combine population-wide information with individual level information. So that's what they call a hierarchical model, where you kind of use the assumption that there are some similarities in the population as a whole. So you can sort of like use what you know about other people to sort of fill in the gaps a little bit. And this is how you can get away with asking fewer questions than you would need otherwise to pin down individuals. So anyway, when I went to work for them, I was originally doing some other stuff, but about a month in, they decided that they were going to start using their own software. There was a company there called Sawtooth Software that made software to do this, but they wanted to have their own software, and they also saw themselves as working on the really hard problems and working with leaders in the academic side of marketing research. Like people like Greg Allenby. And so they wanted to, to like implement other models that are out there in the literature that nobody else was offering. And so they could say that, they were really the top of the line and they had the most recent stuff. So that's sort of where I came in, is that they took some code that was originally academic code and we're trying to turn it into production code. Now, I don't know if you've ever done this, but turning academic code into production code is kind of a nightmare because when you're writing code to write a paper, it only has to work for the data set in your paper. It doesn't have to work for everything, right? It doesn't have to take care of all the messiness. I mean, maybe it has to take care of whatever messiness is in that particular data set, but it doesn't have to take care of the full range of things that can happen. And also, academics don't tend to be all that great when it comes to, code quality, organizing their code and testing their code and all that stuff. So anyway, the guy who was working on it was having some difficulty with it. I started taking a look at it, and now here's where things got interesting. So this sort of gets in the career path. Just because I was interested in the subject, I read a lot about Bayesian computation. It wasn't required for my work or anything like that. I just wanted to know. I was just fascinated by the topic because there's some really difficult computational problems there with Bayesian computation because they involve these huge, essentially integrating over thousands of variables. How in the world do you do that in any reasonable amount of time? So this whole area of Markov chain Monte Carlo as a method of doing that. So I had learned quite a bit about that. I had never actually implemented any of it. Now, I didn't tell them that side of it, that I had never actually implemented any of it. I knew the theory really well, but I had never actually implemented any of it. So we get into this, and I'm looking at it, and so I did the usual kind of things that I'm used to doing, just in terms of test-driven development and making sure everything's well tested, to try to figure out what was going wrong. But I actually found a really subtle bug in the implementation that you have to understand the math to understand why it's a bug. Okay, it turns out that there is a likelihood they were computing using Monte Carlo. So we have Markov chain Monte Carlo, and within the iterations of the Markov chain Monte Carlo, they were doing some just straight plain old Monte Carlo to evaluate a particular likelihood. Well, that's an approximation. It's not quite the right thing, right? And that bit that you're off kind of skews the results to some amount. And so the fact that I knew the theory well enough, I was able to figure out how to actually fix that. Turns out there was a very simple fix for it that will in fact get you it will get you the theoretical right behavior. In terms of a Markov chain, it'll have the right stationary distribution that you wanted to have and everything. And so that sort of got me off on a good foot there at the modelers doing that. But yeah, so I ended up doing a lot of other kinds of stuff like that, implementing various other custom models that were in the literature, doing experimental design, which is actually something you don't see a lot of in machine learning, because machine learning usually just take the data you have, right? You don't have any control over that. But when you're doing a survey, you get to control what sets of questions you ask and to whom you ask them. And so it's important to be able to get the most information per question. And that's what experimental design is all about. Anyway, so I worked for them for several years. Did it. I'm not going to go into all the details of what I did for them, but that was a period of time when we didn't have all the tools we have now. We didn't have things like Stan to generate code for Bayesian models. So I was spending a lot of time like doing the math myself for the Metropolis updates, right? Lots of linear algebra and everything. And so my typical work during that time was like spend days and days doing tons of math, and then about a fifth that much time actually writing the code after I worked out all the math and made sure I hadn't made a mistake anyplace. And then Stan came along, and of course I was really excited about that. Things like Stan and some of the other tools that are out there now. Let's see, what else do I want to say about that? Oh, so after the modelers eventually, like I said, got consumed by Omnicom, and their focus began to be more on quantity over
Say it
quality.
with a voice.
With the voice.
Omnicom.
That's right. Omnicom. Um, and we had what I call the purge of the PhDs. One by one, the PhDs are all let go. Um, I was let go. A few months later, my boss was let go. Um, and a year or two later, the founder was let go. He had sold out to Omnicom. And so by that, because they just decided that was just the mindset of the company that bought them out. So yeah, all the PhDs, all the idea of being the people who solve the hard problems was out the window. Was no, we want to be a project mill. We just want to get as many projects pushed out the door as quickly as possible. So anyway, so where I went after that is I worked for Semantic for a little while, did some revenue forecasting. One of the things that I'd learned while I was at the modelers is I'd learned about state-space models, and of course those have applications to forecasting. So with the revenue forecasting, we're trying to model the whole revenue process, including leads and everything. Um, but I was only there for about 7 months, and got an opportunity to take a more rewarding job, which was Adobe. So I kind of jumped ship at that point, and went to Adobe, which is where we met. And at Adobe, my focus was mostly on various forms of forecasting.
Yeah, and Kevin
Some of
was a
these,
senior staff engineer at Adobe, so not just some, you know nothing that hosts the podcast, but a senior staff engineer.
thanks. But yeah, so a lot of time series forecasting, forecasting load, server loads. There were a lot of sort of one-off little projects for the director, Jan.
Yeah.
In some cases where I had to apply a Bayesian methods to get some sort of answer with very little data. Jan was actually pretty excited about that because he says usually when I ask these data science people, they say, "Sorry, can't do anything about that." It's like, well, okay, we can do a little bit. We can come up with a reasonable prior based on what we know about the situation to sort of limit things a bit. So, yeah,
I,
another one
I
of the reasons why I
remember
like the Bayesian methods.
I remember he once told me that like we don't want to have you in the on-call rotation because like if you don't get a good night's sleep and then like that ruins a lot of really important work. So that's why I got to be on the on-call rotation.
Oops.
But no,
Anyway,
yeah. So tell me about what you're doing now and why.
yeah. So what ended up after that is I have always wanted to. Well, two things went on. I have always wanted to get back into doing some academic research, and I have been very much interested in. And one of the reasons I was interested in Bayesian probability theory was that it's basically epistemology, right? It tells you how you should evaluate evidence and how strongly you should believe, various hypotheses. Well, potentially it tells you that. There, there's some fine details there that we have to work out. But I got interested in some of those foundational questions. In 2003, I'd written a survey paper on Cox's theorem, which is a paper that says, starting from certain assumptions, we can show that something equivalent to probability theory is the only viable logic of plausible reasoning, right? Reasoning about degrees of credibility. Um, but there are some limitations to Cox's theorem. For one, it assumes from the start that plausibilities or credibilities or whatever you want to call it are measured as real numbers and single real numbers. So the Dempster-Schaefer belief function people would come back and argue against that. They might argue for at least a two-dimensional or higher dimensional kind of thing. And it does make some assumptions about sort of functional forms of how things decompose. And in 2017, which is right after I joined Adobe, I published a paper where I showed how to basically show that result with much weaker assumptions. So the idea is that propositional logic that start with propositional logic. Okay, propositional logic will sometimes tell you, given these premises, I can say yes, A is true. Sometimes I can say for sure, no, A is false. And then there are all these other cases where I can't say either way, right? And would like to fill in that gap. Would like to be able to assign some level of credibility, some level of plausibility between certainly true and certainly false. And what are the options? And so all the assumptions that I use in this theorem are basically assumptions of the form, this property that propositional logic already has, and it would be really weird not to have, we're going to keep this property. And it turns out that is enough to show that, again, probability theory or something that is isomorphic to it is your only option. But it actually takes you a step further than that. It tells you how to take a set of propositions, your state of information. There's this notion of state of information that Jaynes talks about a lot, that Bayesian probabilities are not features of the real world. They're features of what you know. They're features of your state of information, right? And they shouldn't be purely subjective either. They shouldn't just be your opinion or your feeling or something. They should be based in something, and they should be based in what information you have. So two people with the same information should have the same probabilities. And so in this case, the information is actually a finite set of propositions. It's propositional data. And we can actually say exactly what your probability should be. Not just that it's going to be the law, not just that you're going to use the laws of probabilities, but we can actually give you a number to calculate. It says this is what the number should be. And that was pretty exciting to me, but it was really restricted to finite cases. So effectively, because it's propositional, right? Propositional logic doesn't deal well with infinities. And what I have done since then is I've worked out some stuff about how to extend it to the infinite case. And again, a lot of what I'm doing here is I'm trying to fill in, I'm trying to flesh out ideas that Jaynes had, but never worked out because he was a physicist, he wasn't a logician, right? And so he talked about what he referred to as the finite sets policy. You always start with finite when you don't want to deal with an infinite set or infinite number of possibilities or infinite gradations of distinctions. You always start with the finite case, and then you take the limit as the number of states or number of gradations or so forth gets larger and larger, so that your infinity is always derived from well-defined limits. And so it's been a few years. I did work out and proves that we can actually a way of defining a metric space of premises, defining what they mean for them to be close to each other, similar to each other, and to really rigorously define what this whole notion is, and to show that. Backing up a bit, the usual approach to probability theory is measure theory, which most of your audience has probably heard of and tried very hard not to study because it gets into trans-finite induction and all kinds of awful stuff like that. I mean, if you're reading through the proofs and stuff, and most practitioners don't really get into the fine details of measure theory. But measure theory is really cool in the sense that it unifies like discrete distributions and continuous distributions or mixed continuous and discrete. It's a very, very nice theoretically clean framework. But it starts at the infinity, right? It doesn't start from the finite and work up to it. And anyway, what I showed was that every computable measure, which from an epistemic standpoint, if we're thinking of probabilities as logic, things should be computable. So anything that you're ever going to actually work with has got to be computable. You can't do anything with it. So any computable measure can actually be obtained in this way as a result of a sequence of increasingly refined finite bodies of propositional information. And so that's sort of a research direction I'm pushing in. The idea is that if we understand the fundamentals better, we really understand that the really ground level stuff, that it will let us do a better job of tackling some of the hard problems in probability theory. So
Okay,
just to
so
give you an idea,
let's talk a little bit about let's talk a little bit about the fundamentals then. Uh, what what is fundamental?
so
Especially to the concept of learning, right? Like you're specifically focused on the probability theory, but like more broadly, like what do you see as the fundamentals of learning?
let's look at the very, very, very simplest problem you can have out there, which is, simple induction. In fact, so simple that we just have a sequence of binary variables, right? And all we want to do that we have, we have no reason to we assume there we assume that there is some probability. No, it's their we assume they're each Bernoulli draws, right? That there's some probability between 0 and 1 that'll be true or false, and that it's independent for each one. Okay, how do we infer that? We don't even have a full answer to that simple question. Okay, so part of the problem is that the usual way we do it is we come up with, say, like a, uh, a beta distribution on that uh, Bernoulli draw probability, right? Okay, where does that prior distribution come from? That beta prior, should it even be a beta prior for that matter, right? The beta prior is computationally the easiest one to work with. It should it even be a beta prior? But what should it be, right? How do we even? I mean, and people just sort of go intuitively and have various intuitive arguments, and in a lot of circumstances we can sort of get away with just kind of fudging it a little bit and saying, well, this looks
Yeah, I'm
reasonable.
so sorry to do this to you, but bitter pill, right? Uh, do we like? I understand why it would be really cool to understand that, right? But do we need to if throwing more data at it will
Doesn't
probably just
always
work?
work
Yeah, it
because
doesn't work. It fails in ways we can't predict, and then we're like, oh, okay, this doesn't work every time. But
here's the problem. What if we have predictors, or what if we have a large number of categories? So it's not just binary, it's categorical. So
Mhm.
think about doing trigrams or quadrigrams or pentagrams or so forth. You quickly get to the point where you have to have more structure there. There's more. You'll never get enough right. You'll never get enough data. You'll never get enough data. Anyway, the point I was trying to make is that one of the things we don't understand is that to give you an idea of why it can be a real problem is this: we don't even know that you can do the induction. If you really don't know anything about these values, right? If you're really truly in a situation where we're dealing with um, what's the word I'm looking for? Not default.
No priors, right? Like,
Well, I mean, there's always a prior, but
yeah,
basically we want ignorance, a true ignorance,
yeah.
right? Well, true ignorance, we don't even know these values are related in any way at all, right? The first one could be whether or not the number of people in the world is even. The second one could be the 27th bit of pi. The third one could be, they could be all the things. They just have no connection whatsoever to each other, right? And in that case, no, it doesn't matter how many of them you've seen, you can't learn anything. That's actually provable. If you have no prior information whatsoever, you can't do induction. You're just out of luck, right? Those values are just all completely independent of each other, and even after you've seen 10,000 of them, you can't use the fraction of them that have been true so far to make any sort of conclusion about what the next one's going to be. Okay, and so I'm trying. So one of the things, like that's just a simple example of like that's a really basic thing that we don't understand. You know, in general, we don't really understand very well how to create priors,
Yeah.
and
And one of the things I learned from you is every time you think you don't have a prior, you do. It's just implied, and so
Yes.
you can't troubleshoot it. You know, uh, yeah, that's
Any,
fascinating.
in, anyway, so actually, I have been sort of semi-retired in that I've been, I've done some consulting work, but lately I am putting a lot of effort into, into that research area and starting to write up results. And I have a bunch of results that I just sort of wrote up enough so that I was satisfied that I knew the answer, but didn't write up into a paper, right? It was not in publishable form, and so I'm doing a fair amount of work trying to get some of that cleaned up and put out there and made more accessible
So
right
how do
now.
you create new knowledge? Because that's, like I've been an engineer my entire career. And that's been I don't have a PhD. I don't have a fancy degree. I have a master's. But like the concept of creating new knowledge, right? Like you're a systematizer. This is terrific. So you can give us a system for creating new knowledge. If I were in my last year of PhD today or first year of PhD today, and I was thinking about ML as a career, uh, how do I do it? How do I advance the state of
Okay.
the art?
Are you interested in advice for someone who's just about to start grad school too? Because I do have a few
Sure.
things to say about
Yeah.
that. I'll
Hey,
say so. Let me tell you
we'll
my
take it.
my big mistake I made. Okay, when I went into grad school, I did not
You didn't talk to
understand.
Bezos enough. Kevin was a year before Bezos in his undergraduate degree, and
Yeah, I almost went to Princeton, which is where Bezos went, but ended up not going there. Um, so the most important thing is your choice of advisor. That's even more important than the school you go to. Is finding the right advisor because you're going to be working very closely with your advisor and realizing that this person is your advisor and his resource that you need to be using. Your next most important choice is a dissertation topic because that needs to be something that is a problem that is challenging enough to be worth publishing and worth getting a PhD for, but not so difficult that you can't solve it within a few years. And this is where a good advisor comes in because a good advisor will typically have far more ideas that they don't have time to pursue themselves, then they can pursue in their own time. And
yeah,
so they've got plenty of interesting ideas that they can toss at graduate students and have them run off and try to solve them. And that was the biggest mistake I made in grad school is that I did not understand that. And I did not do a good job of making use of my advisor or, um, well, in one sense, in choosing an advisor. Um, I, I should have done things very differently than I did.
well, I think
Um,
all of us have that about our schooling, and it's really interesting to me because the advice that you give there is really pertinent throughout the career too, right? Like this is like your manager, your technical lead has way more impact on what you're doing than the company. Like people go to companies because of the company name, and like my favorite is like such and such a company does not have very good work life balance, and I'm like, I've seen managers there whose teams have really good work life balance, and I've seen managers whose teams don't. And also the choice of project too, right? Like I feel like as MLEs we're very prone to picking projects that you cannot complete in a reasonable time frame because it would be really cool
yeah.
if we could do this. But also, like I see less of this, but I see some failures on the side of like this was too trivial. This doesn't actually move the bottom line. Like,
Yeah.
okay, you've done it, cool. I don't care. And so yeah, that's. I think that generalizes after graduate school as well. I think that stays with you forever.
I think there's one more thing that I would also piece of advice I'd also give for a starting grad student, which is that and I'm going to guess that your audience here are all probably pretty bright people who probably sailed through school, are
Hey, if you
used
subscribe to this
to
podcast, you definitely are one of the best and brightest.
are probably not used to needing help in school, right? They're probably used to just going through, they and just working things out. And when you get into grad school, it's going to be a different environment because it's not just doing the homework. It's not just doing tests. It's finding a good, very important part is, like I said, finding a good project to work on. And you need to learn how to ask for help. If you have never, ever, ever had to ask for help before in your academic career, once you get into grad school, you need to accept that there may come a time when you're going to need to do that. And that needs to be in your mind as a possibility. That it's okay to go to your advisor and say, I'm stuck. I don't know where to go. Can you help me out here?
Man, this once
Uh,
again generalizes to professional life because, like working at Meta specifically, right? Like in Meta ads, people come in there, like the bar is pretty high, and so by the time you come in there, you're not competing with whoever you were competing with and like the little startup that you were in or whatever. And so I helped the guy get into Meta last year and coached him kind of through it after that. And he came back to me like a couple of months in, and he was like, I don't know how to get an edge on these people because everybody already is very smart. Everybody already is working like nights and weekends. So like my usual methods of like I'm just gonna outwork somebody or I'm just gonna be smarter than somebody, they no longer work. And yeah, like I mean, this is when you come to people and you ask for help, right? This is where you need to understand how to do that. So yeah, I think that's all applicable way beyond graduate school, and I think that's partly why graduate school is, I wouldn't say prerequisite, right? Like I don't want to gatekeep necessarily, but you do see a lot of MLEs coming from like some sort of graduate school background, be it a
yeah.
master's degree or a PhD. Um,
Well, I think part of it also is that one of the most important things that grad school taught me was just how to teach myself.
yeah.
Learning how to go out and just dig up things in the literature and because I always found that most of the stuff that I needed to know, nobody was teaching any of the classes that were available in the department. so,
Well,
so
that's
what
terrific.
it,
So I have a question for you on that one then. How do you learn new things, right? Like especially like you learn Bayesian stuff from scratch. You learned marketing things from scratch because you were interested in them. Like I remember the reason I think you're a perfect person to ask this is years ago you told me that like, listen, if you know nothing else, go find like the recent graduate student thesis in this, and just read through the introduction section. Like that hack will get you really far. But beyond that, is there anything like how do you read a paper, right? Because I know lots of people who like open up a paper and then close it and they're like, didn't get anything. But like, how do you get stuff out of a paper? How do you get stuff out of the thesis? What resources do you even look at before you even get there? And if you can speak to that, that would be amazing.
yeah, I can't really say that I have a really, you know, full-fledged system. I think the main thing that
And
I've
you
always
call
had going
yourself
for
a
me,
systematizer.
I know. I think the main thing I always had going for me was just plain stubbornness. Like I would start trying to figure something out, and I'd find a few papers, I'd get a little bit, but I would get a little bit, but wouldn't really get as far. I didn't fully understand what I wanted to, and then I'd go off and do something else for a while, and I just, um, but I was too stubborn to give up. Right, and I would come back to it, and it's kind of like the just bit by bit, chipping off bit by bit. Eventually, things start to make sense. Um,
You don't
but
have a
yeah, I mean,
system for reading the papers?
actually not. I mean, there is a little bit of scanning over it in the begin, to begin with, right? Uh, a little bit of, of course, the usual business of going down and reading the conclusion, reading the introduction, and all that kind of stuff. There's the business of using papers. Oh, of using a paper that maybe turns out to not have the information you want, or maybe you didn't understand that well, but it's got some great references to other papers. Like a lot of times, right? They'll reference the seminal papers in the field
Uh-huh.
that introduced the ideas in the first place. So they'll be talking about something that involves some concept you know nothing about, but they assume you do. But yeah, you follow the references, and then that gets you back to the paper that tells you about, you know, the precursor concepts you were supposed to know before you even tried to read that paper.
Yeah. Yeah. To me, if it's like a new enough field, one of the things I would do is I would take a look at a couple of papers that I can find really quickly. and look at the reference section and see if they're all referencing the same paper, and then I'm gonna go read
Wow.
that one first.
So nowadays, there's actually a new strategy, which I go to ChatGPT and describe what I'm looking for, what I want to understand, and not because I want its explanation, although that may help a little bit. But basically, I'm trying to have it help me find the right things to read and find the right terminology. So, for example, when I was first learning Bayesian statistics, an obvious thing that came to mind was that, gee, if you want to be really general and not tie yourself down to a particular parameterized form, maybe we should have an idea of a prior over functions. And then I thought, well, surely someone's already thought of that idea. But I couldn't find anything on it. And it was because I didn't know what they were called, right? They're not called
Yeah,
priors over functions. They're called stochastic processes or stochastic fields. And it was years before I found the right terminology. Several years before I found that, and suddenly I was able to find plenty of information on the topic. But without knowing the right, the magic words, the right thing, the right words to look for, it was very difficult to find anything on the topic. And I found that ChatGPT is really good at that. You say, I don't know the word for this, and then you describe what it is. It can generally do a pretty good job of telling you what the right term is that you should be looking for.
yeah, no, yeah. Just a word of warning to not take like the terminology it's great at, but do not take its explanation, especially of like the newer fields, right, where it doesn't have a
Yeah,
ton of
yeah.
training data at face value. But yeah, I think who
That's
was
why
it?
getting good references and getting terminology, stuff that you can check, right?
Yeah, yeah. Somebody in my career told me that like number one skill is knowing what to Google. If you know what
Yeah.
to Google, you got it all. But yeah, um, so this is like how to learn, but there's a meta problem in machine learning of what to learn, right? Because the, there's a real difference between things that come out all the time, and you sometimes actually do need some of them in your job, versus like this is going to be a seminal paper. I got to understand this, and I'll be honest with you, I'm really bad at this. When attention is all you need, paper came out partly because it was so clickbaity of a title. I was like, "There's no way! Like, this is not serious. This will go away. This is a fad, right?" And it took me about 6 months after it came out to like come around to it not being a fad. When every researcher at Adobe was like, "We're doing this with attention," I'm like, "Okay, now I'm listening." But how how do you know what to study in order to stay relevant in the industry? Like for MLEs,
That
like our stuff moves.
yeah. I mean, so that is a difficult problem, and this is sort of something where you get into the personality types because, like I said, I'm a systematizer, and my tendency is like I want to understand the fundamental issues, but and here's sort of that bitter pill. The advances in deep learning have had nothing to do with understanding deep issues, right? They've all been successful hacks, but they've all been hacks.
Wait, stochastic
And
gradient descent is a hack?
well, kind of, in a certain sense. Um, and there are a lot of things like that just people tried them out, and you couldn't necessarily have predicted in advance what was going to work or what was not going to. And so there's a bunch of things that people know work, but I really do think that we don't really have a deep understanding of why they work, right? And people have been surprised at how well the large language models have worked. And the researchers themselves did not expect them to work that well.
Yeah.
And so there are a lot of things that are really, if you really look at them, are really kind of, they're kind of hacks. They're kind of, well, there's some intuition behind them, but there's not a lot of really solid theory behind them, and that's just the reality. that we've been that we have right now. And I would say one of the biggest mistakes I've made in my career was being very reluctant to look at things like that, right?
So knowing what you
Things
know
that
now, how would you have, like, what would you have even thought of, right? Because you can't chase everything. If you chase every technology that comes up day to day, you're gonna burn out and not be an ML engineer. But at the same time, you can't miss a couple of essential things. Uh,
right.
so like this is a very hard part for me about learning about ML engineering. And people are like, oh, you've been in the area for 14 years. I'm like, so what, right? Like I've been irrelevant 4 times during this time, but like paradigm changed under me. And the new grad knows just as much as I do in the new paradigm, and I have to still commit to learning and do this well.
So
Go ahead.
so are some things that I think there will always be some things that will always serve you well, right? And so learning more math is almost always not going to hurt you. Right? As long as you don't spend, as long as you spend enough time on other things you also need to be doing. But it's like, physicists are sort of like the gods of science because they can go and enter any field they like to and contribute to it because they know more math than anybody else. Right?
Thank you. Thank you.
Oh, that's right. You were from physics, aren't you? I had forgotten that. Sorry, I didn't mean to compliment you.
Ouch.
Anyway, but but no, and so there, same thing in computer science, right? There's some fundamentals that will always serve you well, no matter where things go, and so I think it's always good to make sure you have those down. So yeah, make sure you understand your linear algebra very well. Make sure you understand your statistics and probability theory very well.
Bayesian
But
or
the other stuff
frequentist?
oh, well, you can't avoid frequentist stuff. Obviously, I think that the Bayesian is much better founded and I think has much better possibilities. But the reality is you're gonna have to know some frequentist stuff too. You can't you can't avoid that. Um,
What about, you
what I was
mentioned
gonna
computer science, and what about kind of the fundamentals there that you see as fundamentals?
fundamentals would be things like understanding. Um, you know, there. I grew up in the age right when we had to create our own data structures from scratch. We didn't have all these nice libraries and so forth. So I'm used to understanding like the nuts and bolts, pointers, linked lists, and all that stuff. What's going on underneath there? Understanding how it is that you're able to make a randomly accessible vector uh, that you can append values onto in O of one amortized time. So so understanding your data structures, understanding your basic algorithms, understanding the O of n, O of log n, understanding that time
The big O
complexity
notation.
stuff, big O
Yeah.
notation. Uh, One thing that shockingly few people understand, I found shockingly few computer science graduates understand, is just how to do parsing, how to write just basic compiler stuff. I mean, I'm talking about really sophisticated stuff, but just basic stuff. So I've even found that even just basic pricing shows up all the time. It's very useful, and building little mini tools and little mini languages for yourself. And it just kind of surprises me the number of people who don't understand how to do that. Um, and none of that stuff is really sexy. It's all old technology, right? There haven't been very many new ideas in parsing for years and years and years, but
Yeah.
but it's all basic stuff that's pretty useful to understand. Even
Yeah.
if you're not an expert in complexity theory, at least understanding the idea of yeah, that there are problems that are NP hard, and do not try to solve them. you know, understand we need to throw in the towel and just go with a heuristic.
Yeah. Yeah, no, for sure. And in terms of things changing, right? Like you've been through more than me of this hype cycles and like AI winters and whatever you want to call them. But they're definitely times when it's better to be an MLE than others. So like the late '90s was probably a bad time to be an MLE, whereas 2025 seems like a terrific time to be an MLE. Um, for people who don't like want to change fields every couple of years and are really happy being an MLE, like what do you feel are like some strategies that work both in the lean times and the bad times or in the good times? And
Well, are you talking about on a personal level or a
yeah, yeah,
research level or?
like in terms of thinking about it, right? Like in terms of like what do you need to be concerned with? Are they all that different? Do you just like keep tracking along? Or
Well, I mean, some of these winters you talk about, I mean, we touched on this before, but it's kind of kind of surprising how spring came about. Spring came about just because of more data and more computing power, which is not really the answer that anybody was looking for. At least it's not the intellectually satisfying answer, but it's
Mhm.
and maybe it's not the best answer, right? Maybe we'll eventually find a better answer and find that we could make do with a lot less data, which does seem actually probable considering that human beings aren't trained on nearly as much data as these big LLMs are. But if you got the data, use it.
Yeah.
Um,
I mean, no human being like has the range of knowledge that an LLM does, right? Like the there are different things that we're good at, and in terms of like regurgitating facts, which are mostly facts, mostly usually facts, like LLM is
they're
better
very
than
good at
any human.
truthiness. LLMs
Yeah,
are great at
truthiness.
truthiness.
Yeah, I was at I was at New Rips and I was talking to a group of people, and I said something like, like what LLMs are really good at is confidently BSing, and so the first job that I think should worry about, being automated is a CEO. And the guy standing next to me is like, "I'm a CEO," and I'm like, "Oh, sorry," but but like any place where like confident BSing, like you know, you just sound like you're saying the truth and you don't care that you're not. Like I think that can already be replaced. Any place where you actually have to be
Yeah.
right, like that's a little bit harder.
Yeah, yeah.
So
So what would I say about that? I think part of it is you do even when things are in tougher times. I think it's important to keep on learning, right? Keep on educating yourself. Keep on deepening your understanding. Um, a lot of times, and sort of think about what startups do, right? They start off with this great grand idea that they've got some great solution, and they end up pivoting to something that's actually typically far more specific and narrow than what they start off with, which helps them a lot. And I feel like ML, where if you're hitting it, if things have hit a wall, uh, focusing hard on the specific application areas at hand, the specifics of it, right, and doing well on that, um, and understanding your application area very well, I think is actually a pretty good strategy a lot of times. Um, yeah,
spend
because
all your time understanding it, so when more data comes up, whatever you understood was not relevant, but more data is.
yeah, it's just so that's like how to get through winter. Um,
How do you get through
it's kind of
summer?
how to get through
Because summer is
summer.
also hard, right? Like people don't understand this, but like when you go to social gatherings and everybody is more of an ML expert than you are, and you're like, guys, please listen to me. Like I do this thing for a living, but people have strong opinions, and bosses have strong opinions of things that should be possible because everything is moving exponentially. Why aren't we there yet, right? Uh,
Yeah.
and and so I think summer has some hard parts about it too.
Yeah, yeah. So like when you're faced with a big hype machine, right? Um, I think the real skill is to start asking lots of questions and start probing, because if there's real meat there, there's something real there. As you drill in and try to get specific answers to various questions, those answers will exist, right? the more you drill in, the more things will make sense. On the other hand, if you're dealing with vaporware or BS, the more you drill in, the more frustrated you'll get and less things will make sense.
That's a really good one. That yeah, that's definitely a very good. See, I knew you were a systematizer. I that one is a great system. Yeah, so we're getting close to time, so just a couple more quick questions. I'm gonna cut that out because anytime you say that, people drop out. So I'm not gonna say that. Yeah, no, I think that was a terrific system for how to deal through the summer, how to deal with the summer as well. Um, Having worked on so many ML projects, how do you assure success? Because I think every single person who's ever worked in ML knows how to assure failure. But but not very many people have like shipped successful ML projects and done it multiple times, right? Because lots of demos. I know lots of people who can demo things very well, but it does go back to that, like, you know, taking research into production. The researcher just has to demo that it worked once.
Right.
You have built your career on being the guy who makes it work every time. Uh, what? How do you do that?
Well, so the first part of it is not specific to MLE, right? It's just making sure you've got your software engineering basics down, right? So that you're doing, you've got your unit tests all over the place. You're doing your test-driven development. Um, so you know that you have solid code. Before anything else, make sure that every piece of code, is doing what it's supposed to do. And one of the things that I found especially important there, and one of the things that's it's especially difficult about machine learning and statistical sorts of problems is that most other sorts of software problems, you know the answers, and it's easy to come up with test cases. Whereas with statistical software and machine learning software, erroneous output isn't always obvious that it's erroneous. And so that's always where I have put the most effort in testing. Like
So
if
how do
it's
you test
something,
that?
boy, in a case like that, what I will often do, because often what that involves is like there's some sort of numeric computation. And I had to do a bunch of things to make it more efficient or because the way the data was organized or something. So one thing that I will often do is I will write another piece of code, perhaps in another language, that is horribly, horribly, horribly inefficient, but it's really simple. It is as close to the raw equations as I can make it, right? And it is easy to check, and I will get an answer that way first. Uh, that's one technique that I've used. Uh, Another technique, because numerical, a lot of people don't worry about this, but you know, uh, you can run into numerical instability. And there are numerical analysis issues to worry about. There are a lot of formulas you can use that will blow up in certain regions because you're essentially dividing by one over the difference between two numbers that are very close to each other, right? That kind of thing. Um, and so what I have done sometimes in those is I've gone to a piece of software that has uh, infinite precision or arbitrarily large precision computing, right? Where instead of the 16 or 17 digits of a double, I can have 100 or 500 or 1,000 or whatever,
Well,
like compute some answers to just ridiculously high levels of a number of digits. So I know that even if I have done something, even if there are numerical instability issues there, that I still have the right answer, and then make sure that my code of course, think about ways that it can happen. Think about regions where things can go wrong and how to deal with that. And so my code will often have if then else's to handle different regions of the input space because I have to use a different formula in different regions of it. You sort of have this piecemeal thing where it's like this formula works well in this region, this formula works well in this region, and they overlap by somewhat, right? Um, but there are points where either one of them will just fall down really badly. Uh, there's also just finding a few really simple cases where I know what the answer is supposed to be. Um, with machine learning, there's the obvious thing of like um, starting with the answer and generating the observations
Mm-hmm.
and seeing if you can get the answer back. If you get back the parameters that you use to generate the false data from, the synthetic data from, things like that. Um,
Yeah. The thing you taught me
things,
about synthetic data is only as good as the stuff that you can think of, but
yeah,
it's still worth doing, right? Because like you can already think of a way it's going to fail, so you should check it against that.
yeah. So there's all that. The other thing is never trust your inputs. Again, that's a general software engineering precept, but it's especially important in machine learning. Dirty data is just ubiquitous. Don't assume they make sense. Check them, make sure that they do make sense. Make sure that any assumptions you're making about that data actually hold for the data. Um, and of course logging, right? This is all just standard software engineering stuff. Uh, if you're building any sort of server or anything like that, you're going to want to have sufficient logging there to let you track down what may have happened. Beyond that, and I actually have to admit that I have not always been very good at this. Um, I do have certain perfectionist tendencies that get in my way sometimes, and really, what you want to do is you want to get something that works, even if it doesn't work very well, but something that works as a baseline, and then iterate on it, so that you always have something available. Uh, and that is probably the most important, more ML specific piece of advice I think I can give,
Yeah, for
because
sure.
there's there's
No, and
there's no end to the amount of there's no end to the amount of tweaking you could do, right? No end to the amount of little improvements you could do. So get a baseline there. If you're satisfied with it, you did too much. It should hurt.
I had one time in my no, two times in my career when I wrote a relatively so I don't do test driven development as much. I often test like after the fact. And I've had a couple of times in my career where all the tests ran the first time and like it just worked. And I got to tell you, I was never as scared as those two times because I'm used to it failing, right? And so when it's like, oh, that worked. What did I do wrong? You know. uh,
did you ever have? Because I have had the experience where like everything passed, and it's like when I dug into it, it was because my tests were wrong.
well, yeah, that's
my,
the first
my
thing you
tests were
check. You're like,
flawed.
yeah, did I put assert true everywhere? What happened?
Yeah.
Yeah, no, for sure, and it is definitely an interesting experience. And I think this is a thing. Since we can't guarantee, it's not that we can't guarantee that everything works. It's that I'm telling you that what I really did is I just like took a little bit of data, put it in a bucket over here, just didn't do anything with it during the training, and then let's see like if it even performs well. Okay, it did on like 90% of it, so that's pretty good, right? Like it's wrong on the 10% of it, but it's right on the 90, and I feel like that's a pretty unique thing in our field. There are very few other places. There are very few other like engineering disciplines where it's like, man, this bridge falls down like one time out of 100. That's okay, right? Uh, and like for reasons that I sometimes don't even understand. Uh, that yeah, it's a thing that we deal with uniquely.
Yeah. Yeah.
So anyway, I do want to be respectful of your time, but before we go, this has been a terrific conversation. I always love having conversations with you. I hope there are a few folks
Thanks.
who want to learn more about what you're doing and follow you. And so, what's the best way to keep up with Kevin?
Well, these days I am doing most of my writing on my Substack blog, and that is epistemicprobability.substack.com.
You
So
wish you had a shorter
epistemic,
name, don't you?
yeah, epistemic, EPISTEMIC
Yeah.
probability, all
There
one
will be a
word,
link in the description
.com.
too, but yeah, for the masochists in the audience, feel free to type it in.
And there's a lot of math in there. It's not your typical Substack blog. There's quite a bit of math in there, but I am trying to make it as accessible as I can. And if you do go there and visit, please don't hesitate to ask questions. To put questions in the comments if there's anything that doesn't make sense to you.
Terrific. Thank you, Kevin.
My pleasure.